All right, so I'm going to record um, a few example problems to do with magnetism this week, just so we can do more than what was done in discussion the previous weeks, and so I could go over the question that a lot of people were emailing me about in regards to Chapter 9, Problem 15. So I'm going to do 4 problems. 2 of them, the 2 from Chapter 11, are shorter. So this won't take too long, but again, as I said, it would be about an hour. So hopefully we can get them done though. So, all right. So with this problem from Chapter 9, it tells us that there's a current flowing along the z-axis, up the z-axis. So let's imagine this is the z-axis and I is flowing that way. And there's a sphere with radius r. I'm just going to draw the top of the sphere. And there are electrodes on the front of the sphere and the back of the sphere where the current is going in and out of. And they have an angle alpha. So really, if it's the entire sphere, this is an angle of 2 alpha, right? Because we have this whole sphere. Kind of looks like a potato there, but all right. So we have that, and we want to know. Oh, and let me put the conductivity as sigma. We want to know what the resistance of the sphere is, right? So just starting out, we know V equals IR. So we're going to need to find the potential V. Okay? Now to do this, we can find, well, really it's delta V. We're going to find the potential at the location R, where theta is equal to pi, and we're going to subtract from that the potential at R, where theta is equal to 0. Okay, and that's going to give us our potential difference. So we need an equation for potential, basically. Now, this is spherical, so we can start with the azimuthal symmetry spherical solution for Laplace's equation. Remember, Laplace's equation is this. So we need a solution, which will be this. Okay. So we also have the electric field, and the boundary conditions here have to do with our electric field. Okay. And that's because we have our current. So the electric field at R, for example, is always going to be 0 except for when R, except for when theta is not in the electrodes. So when theta is not, let's say, let's actually do it this way. Let's say when theta is less than, no, when the absolute value of theta is greater than alpha, but the absolute value of theta is less than pi minus alpha. Okay, so basically, if we were going to highlight what region that is, this whole region here, this whole region here, there is no electric field. Okay, but we should have an electric field coming through there because there's a current. So the current is the conductivity times the electric field. So we know that's a boundary condition, right? So we can find the electric field. The electric field is negative gradient of the potential. And we're going to leave the potential as our expansion for right now. We don't have any more information beyond that. But we do know that the radial component of the electric field is all that's really going to matter. Because really, I should say the radial component is equal to 0 there. But that's all that's really going to matter, because we can simply just apply this. Oops. Didn't mean to underline that. This. Right? Because the direction of J depends on the direction of E. So in that case, we'll do it this way and take the partial derivative of the potential with respect to R. And what that does is it lets us write this solution or summation, AL to the R, L minus 1, and then your Legendre polynomial. All right. So now we're going to multiply both sides of this equation by sine theta, Legendre polynomial of some other, with respect to some other indice, not L. So we could say L prime, for example, or K or M, whatever, however you want to say. So we're going to do is we'll do sine theta, P, I'll say L prime, cosine theta is equal to negative LL prime. And these really should be two summations, but it's not too important, and you'll see why. So we have this, and then we have the sine theta term and the PL prime cosine theta term. All right. Okay. So now what we're going to do is we're going to integrate both sides of this using u is equal to cosine theta. All right. So we're going to integrate both sides. Okay. And this is the reason we included the sine term, because when we use the u substitution, right, we get that sine term out. Right. So doing this lets us integrate with a bound of -1 to +1, because normally our bound would be 0 to pi, right? So we can do -1 to +1. ER evaluated, and again, this should be, we're trying to evaluate at the surface, right? We want to find the surface term, so now we're going to evaluate there. We're going to take R is equal to R, and R is equal to, little r is equal to big R. Not theta. U, right? That's our substitution. And then we have PL prime U du. And this is equal to negative. I'm actually going to drop the summation just because it's going to be a little more clear. To the big R to the L, because we're evaluating at little r is equal to big R at the surface. And then, again, we have -1. We have PL u and PL prime of u du. Now, this is the integral that gives us the orthogonality, or this is the orthogonality of the Legendre polynomial. This is equal to 2 over 2L plus 1. Delta function of L minus L prime. Right. It's the orthogonality relation. So this is telling us that L and L prime have to be the same. All right, it's basically what that's doing. So we can solve for A. AL is equal to negative. Oh, and I accidentally lost the negative from up here, so there is a negative here. Negative 2L plus 1 over 2. And then we have the 1 over r to the L minus 1 term. And then we have our integral here. RU, PLU, DU. Right? So that's what we have. Okay. Now again, right, we said earlier, JR is equal to conductivity ER. So we can also solve for ER here at the surface, right? This is evaluated at the surface. And this is important because we're going to be able to plug it into that integral. But how we do this is we say JR over conductivity sigma. This has to equal depending on what direction or what side of the electrode we're coming in. So when we're coming into the sphere, it's going to be a negative sign. When we're leaving the sphere, it will be a positive sign. So I'll put both, but that's why we have the plus minus I over sigma. And since this is a J current, we have to multiply by pi and then R alpha squared. Right? Because that's the area that is being looked at, basically. All right. Okay. So now what we can do is we can look at that integral here. All right. And the reason we want to look at this integral is so we can plug it back in to our expansion for our potential. So we're going to look at the integral. ER PL U du. Again, that ER is evaluated at the surface, but I'm just going to leave it like that. So this has to equal plus minus I over sigma pi R alpha squared. Negative 1 to positive 1, PL U du. Okay. From here, all right? From here, you want to use the given hint, right? The given hint value, basically. Now, before you do this, we have to realize that this P, the plus minus is going to depend on the bounds, right? So these bounds here are not really correct right now. These would be incorrect bounds because, like I said earlier, the minus is when we're coming into the electrode. The plus is when we're leaving. So really what we should say is this is equal to I over sigma pi R alpha squared. We're going to have two integrals. One from cosine alpha to 1. And this is going to apply onto PL U du. And minus, so this is where the minus sign from that plus minus comes in, from negative 1 to pi minus cosine alpha. Again, these bounds are from this right here, right? This would be pi, or when you put it into a cosine, negative 1. This would be 0, or when you put it into a cosine, 1. So that's why the bounds, remember, we substituted cosine theta with u, so that's why the bounds are in terms of 1s and cosine of alpha and stuff. All right? Okay, so we have this. Now you can apply the given hint And the given hint is, let me find it in the problem. The given hint was 2L plus 1 integrated x1 to x2 of PL of x dx is equal to PL plus 1 x minus PL minus 1 x evaluated at x1, oops, I got those bounds backwards, x2 and x1, right? Okay, cool. So, what does that look like? Well, first of all, they're both going to, gonna divide by the, that 2L plus 1 term, right? Because we don't have that up here. We don't have that, so we have to divide that out. So then we're going to have PL plus 1 of 1 minus PL minus 1 of 1 minus PL plus 1 of cosine alpha, and really this is a quantity, minus PL minus 1 cosine alpha minus PL plus 1 pi minus cosine alpha minus PL minus 1 pi minus cosine alpha. So there's a lot of writing right now, but we're getting there. Like this. All right. So we have that. And this simplifies, right? Obviously, it's going to simplify a little. But what we can do with these minus ones, especially, and with the pi cosine, is we should note this. Okay? To the L, sorry. So if you put a negative value of u inside of your Legendre polynomial, you can take that negative out and just raise it to the power of L. So what that's going to do is going to give us a difference whether or not we're odd or even. If this is odd, right, if L is odd, then this is going to stay negative. But if L is even, right, if L is even, then what that's telling us is that PL of negative u is equal to PL of positive u. And you can see if that's true, then all of this is going to cancel, because we have PL plus 1 of 1, but we're subtracting it from down here, right? This would just be PL plus 1 of 1 as well, but it would be minus of that. And same thing with all four of these other terms. So if we take L as even, this whole integral vanishes. So we're going to take L as odd only. All right. So we're going to take L as odd. And if we do that, the integral becomes I over sigma pi r alpha squared times 2 over 2L plus 1. The 2 coming from summing everything after you, like I said, I'm simplifying this. So after you apply that condition for the negative value inside, you're going to get a 2 out on top. Again, we already had the 2L plus 1 up here. And you're going to have PL minus 1 cosine alpha minus PL plus 1 cosine alpha. All right. Again, this is if L is odd. Okay. All right. So now we plug all this back in, right? And really here, well, we'll see. But we're going to plug all this back in to our original expansion for the potential. And what we get, because remember this was part of A, is phi r theta has to equal I over sigma pi r alpha squared. Okay, and again, we're taking L is odd. So what we could also do is you could just put it as 2L plus 1, right? Same thing, but I'll just take it as L is odd. And then what you have is R to the L plus 1 over R to the L minus 1. And this is evaluated at big R. And you have 1 over L. And you have P L plus 1 cosine alpha minus PL minus 1 cosine alpha. And this is all times PL cosine theta times PL cosine theta. So again, like I said, you could rewrite this using, like for example, in, let's say phi is r and theta is equal to I over sigma pi r alpha squared. Let's say n is equal to 0 to infinity. And this would be 1 over 2n plus 1 r to the 2n plus 1. And sorry, I made a mistake up here. This should just be L, obviously. Divided by r to the 2n times the quantity p2n plus 2 cosine alpha minus p2n cosine alpha times p2n plus 1 cosine theta. Okay, so you can write it like that as well. Either of those is acceptable and fine. Now we get the potential difference. Again, I said this at the very beginning, but you apply it at capital R at the surface, right? Because we're getting the potential difference between the two electrodes. R and theta minus phi r and 0, where theta is equal to 0. Okay, so this is equal to I over sigma pi r alpha squared. And I'll just leave it in terms of n, just because I already have it written right here. Right, if we substitute in the big R, then this just becomes R over 2n plus 1. These cosine alpha terms stay the same. All this stays the same. All this would be factored out, right, of each of these terms. The only thing that's subtracted really is the theta dependent terms. They're the only things that can't be factored out. So this would be cosine of pi, which is negative 1, minus e2n. Sorry, this is 2n plus 1, minus p2n plus 1 of positive 1. And this, all this is equal to is minus 2, right? Because we're saying they're odd, so these are opposites each other. So this is negative 1, and this is minus positive 1. So it just cancels out. Well, they don't cancel. They sum together to be minus 2. So this whole thing is 2I over sigma pi r alpha squared. Summation n is equal to 0 to infinity, r over 2n plus 1. And then the two Legendre polynomials with cosine alpha. Okay. There's a negative here. So what we can actually do is just factor that negative in. Like that. Okay. So now, like I said, using Ohm's law, V equals IR, we can just write R is equal to 2 over sigma pi R alpha squared. This is resistance R, not radius R, right? N is equal to 0 to infinity. Radius R over 2n plus 1, P2n cosine alpha minus P2n plus 1 cosine alpha. And that is our final answer. Okay, this is the total resistance. Okay. All right. So the other part of this problem wants us to evaluate as alpha approaches 0, right? Well, as alpha approaches 0, cosine of alpha is going to approach 1, right? But also consider the term where n is 0, right? If n is 0, we have p of 0 of 1 minus p of 1 of 1. So you have a 1 minus a 1 here. So the resistance diverges, okay? And your resistance is diverging. You can think of it physically. So R, we can say diverges. Physically, let's consider that. So if alpha is decreasing, right? Alpha is getting smaller and smaller. We're attempting to put that current I through these electrodes. Well, if the electrodes are vanishing, there's nowhere for the current to go. So in physically, what that means is the resistance is going to diverge to infinity. You have to have infinite resistance. And eventually, if alpha is 0, then no current is going to flow, right? So that's the limit, right? If alpha approaches 0, then no current will be able to go through, and you just get exactly what you would expect, which is the resistance diverges in that case. Okay. All right. So that's the problem that everyone asked about, or several people at least asked about. Now I'm going to move on to the other things in chapter 11 and 12. So this is the problem from chapter 12. This problem is actually a really good one because it has us look at the magnetic moment. We got to look at magnetic field. We got to look at the vector potential. So it's putting a lot of different things together. Now, before we do anything, we need to think about how we find the magnetic moment. So the magnetic moment is 1/2 R cross J, and this is the volume integral, integrated. All right. So to get this, we need to get J, right? So J is nabla cross B, or the curl of the magnetic field, which we can rewrite again as magnetic field as the curl of the vector potential. So we're taking the curl of a curl. So let's start with the vector potential's curl in this case, right? I won't write out all of the stuff there. Also, I forgot the mu naught here. The entire curl, but right, you can do it tabularly using the matrix, or the matrix way, I should say. But we have this e to the negative lambda r for some value of lambda. We don't know what it is. So if we take the curl of this, you're going to have an r hat term and a theta hat term. Okay, which makes sense. This is phi hat. This would be listed as a phi hat or a phi. So if you take the curl of this, I'll just write it u naught a0 over 4 pi. Okay, that comes out because those are not going to be differentiated. But in the r hat term, you're going to have 2 cosine theta over r squared. And I'm going to actually go on and let me go back a little. I'm going to go on and pull this out because even though we differentiate it, it's an exponential, so it stays around, right? Plus the theta hat term, which would be lambda sine theta over r, right? And again, that lambda is coming from the exponential, okay? All right, so that's the first curl. Now we need to take the curl of this. So j is going to be 1 over mu naught nabla cross b, right? So this was b. And if you do that, you're going to get back out a phi hat term. That's what you end back out with. It's going to be slightly different from what we started with. Obviously, it's going to be different. But it's interesting that's what you end back out with. So this is equal to phi hat 4 pi a naught sine theta times 2 over r squared, r cubed rather, 2 over r cubed minus lambda over r, lambda squared over r, e to the negative lambda r. Okay, again, doing the same exact thing, taking the curl. All right, so from here, we can now find the magnetic moment, right? So the magnetic moment is 4 pi a naught, a naught over 4 pi, not 4 pi a naught. Let me go back. A naught over 4 pi, right, times 1/2, times, or integrated, r cross, let me do it this way. Let me write it out this way. Sine theta 2 over r cubed minus lambda squared over r, e to the negative lambda r, r cross phi hat. Right, so this is just r hat cross phi hat. And r hat cross phi hat is negative theta hat, right? I think I showed you all, or you should be familiar with this kind of cross product unit vector kind of circle for each of your coordinate systems. So this is saying r, this is saying r crossed with theta equals phi. That's how we read that. So r, if you go against the arrow, you get a negative sign out. R crossed with phi equals negative theta. Okay, so we get a negative theta term. I'll just rewrite it here as negative theta hat r. This is d cubed r. Okay, so what we can do is integrate this or replace this theta hat as a Cartesian coordinate. You should do this because the integration is going to be simpler. But what it also does is it lets you notice that only a portion of the Cartesian plane will survive. So in this case, it would be all of theta hat, all of the theta hat direction, but it's really only going to be oriented along a Cartesian unit vector. So what we can do is we're going to write theta hat out. Theta hat is x hat cosine theta cosine phi plus y hat cosine theta sine phi minus z hat sine theta. Okay? All right. Keep in mind, d cubed of r, if we do that, you get, right, a sine theta term. This will be r squared sine theta, dr, d theta, d phi. Okay? So what we can do is we can write all this out, right? So think about, as we've done before, like a sine theta times a cosine theta, or a sine theta cosine theta integrated from 0 to pi, that would vanish, right? Or you can think about the phi term, even the phi term. That's just as good, because actually it's better, because the phi terms here, it's the only thing that depends on phi, and phi goes from 0 to 2 pi, so cosine integrated from 0 to 2 pi, it's going to vanish, right, in the y and the x. So all we're left with is the z hat direction. So the dipole will be negative z hat a naught over 8 pi. And this is integrated well, we'll go on and write all of them. 0 to infinity for r. This would be sine squared theta, right? R cubed from the r squared from putting in the volume, infinitesimal volume. 2 over r cubed minus lambda squared over r, e to the negative lambda r. Okay, I think that's all our terms. Right? I believe so. Okay. What you'll notice if you integrate this is that this also vanishes. And really it vanishes as a result of your r integration. But overall, this is still going to vanish. All right, so there is no magnetic dipole here. Okay, and that's all this exercise is kind of showing. So you could just stop there if you wanted. Even if you integrated up here, I believe you still should get an integral that vanishes. It should be sine cubed of theta. But yeah, it's going to vanish. Okay, and that's all this exercise is showing. All right. There's a lot of curl practice here that you can do on your own if you feel not super good about the curl. With the curl, right, let's just write this. Let's say dx, dy, dz, something like that. So with the curl stuff, sorry, I wrote this on the wrong line. Let's do x hat, y hat, z hat, dx, dy, dz, ax, ay, az. I'm sure everyone has seen this. I think I introduced it the very first week of class, just in case you didn't. But with the curl, you can always use the matrix kind of determinant method, where you just take x hat and then you look at this lower quadrant. So we're going to take the dy of az, we're going to take the partial derivative with respect to z of ay. And then you're going to take minus the center one, so this would be plus, minus, plus. So x hat dy az minus dz ay minus y hat dx az minus dz ax, on and on and on. Okay, and obviously if you're in the other coordinate systems, you have to put in your kind of what's the word I'm looking for? Like your 1 over r squared term or your 1 over r squared sine theta term, right? You have to include those, okay? All right. So now I'm going to do this problem. So we're going to show, again, that there's no dipole moment, basically. All right. So what you can do with this problem is you can do it the exact same way we did 11.1. You can go through, calculate the curl of A, and that will give you B. And then you take the curl of B, and that will give you J over mu naught. And then go into the integral form of as before. But what you can also do is use this, which is given in Zangwill as example 11.1. So this is just another, I'm going to show you another way of doing these problems. Okay. You can use this identity. All right. T tau B. Okay. All right. So this is the vector potential, right? AR is equal to some function f of r times the vector r. Right. Okay. So you can use this identity. We're going to start here. And now what you can do is use the form of the vector potential, right? Nabla cross A d tau. And you'll use a form of your divergence theorem where now we're going to take the surface integral. This transforms into the integral across the surface of a sphere. And it's going to be dA cross A. So we can rewrite this. 3 over 2 mu naught. This is the surface of a sphere. Again, like I said. And this is dA cross F times R. Now this, your surface term here, right? Your surface term is in the r hat direction. Or your infinitesimal surface area is in the r hat direction. Right? If this is a sphere, we take a section of it. That unit vector is r hat. Well, r hat crossed with some function that depends on r times that brings out a something, whatever. It depends on r. And your r vector, well, overall, this is f r hat. Right? R hat cross r hat is 0. Right? That's what we have. So that is going to be that's how we get the answer out. Okay? So f r r hat cross r hat dA. That vanishes. So this is 0. Again. Okay? That's another method of doing it. Again, you could still do this problem doing the same thing we did before if you wanted. And you could get it out in the same exact way. Okay? If you did it the method we did before, then I believe you would need to use like an identity of, because you have a function that depends on r, so you would need to use, basically if you do it the other way, look at section 11.6.3. Okay. if you do it the way, because there's an identity in there that's important for the fact that you have this. Okay, that extra function term, because you're going to have nabla cross r cross the gradient of f at some point. You're going to get that. And when you get that, you have to be able to solve that out. So this is going to be negative r nabla squared f plus nabla f plus the gradient of r of f, like that. All right, but you get that using the, you can get that using the I guess it would be an identity, or like the equations they give you in section 11.6.3. All right. Okay. So the last sort of example I wanted to go over was this one from chapter 12, because I think it's a nice shorter example. Okay. And it's about the Hall thruster. So this is you imagine that you have a electric field going along the z-axis and a magnetic field radiating outwards along the r hat, or since it's cylindrical, it's the rho hat or s hat axis. And we're going to imagine that they exist in a volume V between concentric cylindrical shells. So they're between the two shells. And this volume is filled with some gas, and it discharges and ionizes that gas that's composed of a electron per unit volume, so that is your electron density, and your ion charge, or ions per unit volume, which is going to be, we're going to assume it's a perfect plasma, so they're equal. So this is a model, all right? And part A wants us to show that the electrons drift at a constant speed along the z-axis due to a resulting velocity that they get. So this is the Hall current density, all right? And this is an important kind of aspect, all right? This is very important. Okay, so what we can do here is we're going to look at first, we want to look at the force density acting on the electrons. All right, so we're going to get a electron drift, and this is kind of getting into like 222 plasma stuff. You get electron drifts. But these electron drifts result from, in this case, we're going to result from the electric force density acting on the electrons canceling the magnetic force density acting on the electrons. So how does that work? Well, the electric force density would be negative QE, so the charge of the electron, times the density of the electrons, E, right? The Lorentz force density would be negative QE V cross B. This is just your Lorentz force. Nice. But the density is because we're adding in the density. But we're going to impose that these have to equal each other, right? Oh, FB or FL, whatever you want to say. So what that means is that the electric field is going to be equal to V cross B. Negative. Okay. So, because we're saying they cancel each other. So, what we can do is we're going to say E cross B is then equal to V cross B, negative, cross B, right? Which is equal to VB squared minus B dot. All right, what does all this mean? All right, well, now we can solve for V, right? Because this term here is 0. Okay? Because we know the velocity has no, we're by definition, we're saying it's not in the direction of B. Okay? So we know that term is 0. So now we can just solve for V. So this is a very short kind of derivation. All right. But that's all we have. All right. So this, in plasma, this would be your E cross B drift velocity. All right. Okay. So your Hall current is just negative E and E times this. E cross B over B squared. Okay. All right. So now for part B, we want to argue that the shells experience some kind of force because of the ions being ejected. So we want to look at the force from part A. Well, the ion force would be the charge of the ion times the density of the ion, the force density, times E. But we know this is also equal to QE in E times E. Right? So the forces of the ions being ejected are going to be equal and opposite to the other force due to the electrons, force acting on the electrons. So this has to equal negative E and E, V cross B, using that this equation that we already showed, right? So using the Hall voltage here, we can just rewrite this, right? All this is J Hall crossed with B, right? So, good with that. This force, the force on the actual shells has to be negative of this force, right? And that's just because the equal and opposite forces, right? So if these are this is the force of the ions being ejected, well, the force acting on the shell, we'll say the ejected force, or it gives a thrust as T. This force has to be negative Fi, which is just B cross J Hall, right? So if the magnetic force, though, would act on the ions, then this would change the answer because the ions would be curved, right? So we're assuming the electric force is what's taking over mostly, and that's just because ions, right? The mass of an ion, we're assuming, is much greater than the mass of the electron. So the magnetic force, the Lorentz force, can't act on it as quickly. The momentum of the ions, it takes a lot more force to move the ions, right? That's all it's saying. Okay. And so we've got that out too, just as expected. So the Lorentz force would be low or negligible. Okay. All right. So, sorry, I was just reading my notes to make sure. All right, so that is the video for today. I wanted to quickly talk about the final. I'm going to host a final review session, right? I'm going to send out a form or a when is good like survey for you all to fill out. That's just to see if we can find a time that works best for everyone. The final review session will be recorded. I'm hoping I can get a room reserved for that time, so that's why I wanted to also do it, at least have it done before early next week, so we can have a room reserved by the end of next week, so we can have at least somewhat in person. I'm going to bring the iPad so I can project everything on the screen. I'm also thinking that's how the discussions are going to go next quarter as well, just because I think having the iPad writing while being able to look at everyone and see everyone's questions and answer them quickly is better anyways. So I'll do that, and so that way they'll also be recorded, right? So that's the plan at the moment for at least next quarter as well. Okay. I think that's kind of everything I wanted to cover. The quarter is ending out quickly, right? The material for Poynting vector that we're covering in lecture, that's important. And I think next week during discussion, I'll kind of go over that a little. The Poynting vector, not too much about it. I mean, it just tells you how power flows, basically. How the energy is flowing through the system. One over mu naught. Or this, right? So with the Poynting vector, I think it's important if you're able to show like the direction, but it comes about more so when we're talking about waves. But even then, it helps us to be able to identify like what is the direction of energy flow, right? And that's important. Okay, just in terms of being able to kind of physically think about the physics behind it, I should say. All right. So when you're thinking about like, let's just even think about a circuit, right? Like this. Well, in this circuit, right? If this is our current, the electric field would flow down here, right? It would flow down. And then your magnetic field would flow around this battery, right? Well, crossing those two gives you a Poynting vector, which I'll color in blue, that is radially outward from this battery, right? All along the center portion of this circuit here, your electric fields would be flowing like into the page there, right at the center. I could even kind of draw like, let's do it this way. Let's draw like a slice of this whole thing. So your electric field would be flowing into the page there, right? So this is like a slice of that. And then your field lines would kind of curve a little. So your electric field lines would curve around like this and like this, right? Because that's just what they'll do. Oh, sorry, this is the magnetic field. Magnetic field, obviously. Obviously the magnetic field. It's curving around the wires. Sorry. I don't want to be too like ambiguous with this. But then the electric field is pointing into the wires. Okay? Towards the wires. Right? Towards your wires. And then your pointing vector, regardless of how you're looking at this, or which point you're looking at, your pointing vector is always going to be pointing towards the right. Okay? It's always pointing to the right, which is interesting. Okay? That is an interesting result. Right? And in the center, right, your electric field's pointing down. But that's interesting. And then at your resistor over here, your pointing vector would be pointing towards your resistor on all sides. So overall, if we wanted to like show this, let's say our resistor is over here. The pointing vector is showing that power or energy is flowing from your battery to the resistor, which is exactly what you expect because if this resistor is a light bulb, right? That's kind of what you're going to expect. So this would be like if we're looking top down at the battery, your battery's over here, and then both the wires are running like that, right? So that's an interesting result, okay? So the pointing vector stuff, that's more so what's important is kind of thinking about how its direction, but you can always get it with this formula. And it will come up more when we talk about electromagnetic waves because the pointing vector tells you that it goes in the same direction as the direction of propagation of your electromagnetic wave. All right, so if this is your electric field, let's say vibrating in the X, and then your magnetic field, let's say vibrating in the Y, then your direction of propagation is along the Z, right? That's also the direction of your pointing vector. Okay, so that is why pointing vector is important. Okay, that's the crux of it, and it will come up more, like I said, when we talk about waves, and we talk about like dispersion relations. Right, that's going to be later, and that will be important. Dispersion relations definitely come up in 210B and often on the comp. All right. Okay, so that will cover it for today. Just a little extra thing at the end. But if you all have any questions on the coming homework or anything, just send me an email, and I will email you back. All right. Okay.